Welcome back, and this is more about the transpose. Now that we're on part 2 of the journey, we're going to be leaving behind the world of determinants for brighter reality. So, we're going to talk about a concept I'm calling a vanishing polynomial because I haven't seen a name for it. The concept is this: a vanishing polynomial is a polynomial of a linear map. So I'm going to say P is the polynomial, F is the linear map, that sends the linear map to the zero map. And I'm going to say it's the n by n zero matrix. That's what the zero map means here. So first thing you make clear, what is a polynomial of a linear map? Here are some examples. One example is f squared plus f. That is a polynomial. So here we are actually adding linear maps. We're adding matrices. And f squared means we apply f and then we apply f again. It's f composed with f. In other words, f matrix multiplied with f. And f to the 0, in this case, is the identity matrix or the identity map. So a polynomial of f is an expression involving powers of f added with some other powers of f, possibly with some scalars in front. So another example would be 2 times f plus 3 times the identity matrix. And polynomials of linear maps have some amazing properties. By amazing, I mean they're almost exactly the properties that you would see from polynomials of the real numbers or the complex numbers. And that's because matrices or linear maps satisfy the same algebraic properties as real or complex polynomials. In particular, we have an addition operation that is associative and commutative and whatever. We have a scalar multiplication operation for the coefficients. We know we have a multiplication operation, which is kind of powers, and we know that there is also a distributivity, which is that matrix multiplication distributes over kind of matrix addition. So let's go back to vanishing polynomials. Vanishing polynomials takes a linear map and sends it to a map that sends everything to 0. So it's almost like it's made the map vanish. Vanish in the sense that if you send anything to the map, it vanishes. It makes it into a black hole in a kind of cool way. So vanishing polynomials, it's kind of interesting concept to think about. And once we start thinking about it, we realize a connection with eigenvalues. So suppose we had a vanishing polynomial and we applied it to an eigenvector of f. And maybe we're playing with this concept and we're like, oh, let's do this because we know that eigenvectors and eigenvalues are special things for a polynomial. I mean, for a linear map. So let's get a new sheet. Let lambda v be an eigenvector pair of f. And let p be a vanishing polynomial of f. And let's let p of f be equal to be some kth degree polynomial. That's going to look like a sub k f to the k plus a sub k minus 1 f to the k minus 1 plus dot 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 plus a sub 0 f to the 0, which is identity. So all of these a sub whatevers, they're scalars. And they're the coefficients of what's going on in the polynomial. Okay, let's try it. So if we apply the result of the vanishing polynomial to the eigenvector, first we know that it's going to become 0 because we have a vanishing polynomial, so everything should go to 0. But we could also expand it in a second way, which is if we take the entire polynomial, put it through, we notice that whenever we apply f to v, we scale v by lambda. So if we apply f to v k times, in other words, f to the kv, we get lambda to the kv, because we're scaling v by lambda k times. So actually, the result of applying this polynomial is scaling v by a polynomial rather than applying a linear map to v. So the f to the k becomes lambda to the k. F to the k minus 1 becomes lambda to the k minus 1, etc. And the identity kind of does nothing. So these two are basically the same expression, except one of them is the polynomial evaluated as a scalar lambda, and one of them is the polynomial evaluated at the matrix or the linear map f. So I'm actually going to write this as p at lambda scaling v. Okay, so let's see what happens once we tidy that all up. So what we just showed was that applying this polynomial to v gives us this. Okay, so we have that the polynomial evaluated at the eigenvalue lambda scaling v, the eigenvector, is equal to the 0 vector. And in this situation, we have a scalar scaling a vector to be equal to 0. And the vector is a non-zero vector because it's an eigenvector. So if we're scaling something non-zero to become 0, that's only possible if the scaling factor is 0. You might think of this as the null factor law for scalar multiplication of vectors. So this implies that the polynomial evaluated at lambda is equal to 0. So what this means is that the eigenvalues of f are a subset of the roots of any vanishing polynomial p, because we just showed that any eigenvalue lambda is a root of the vanishing polynomial. Okay, so now we have this. And let's keep our eyes on the prize, which is that we want to show that the eigenvalues of f is equal to the eigenvalues of f transpose. And we're going to make a second observation about polynomials, which is about how polynomials play with transposes. They actually really like each other. So suppose we had a polynomial, let's take that p again. Suppose we had a polynomial p and evaluated it at f transpose. Then what we would get is, well, the expression we had earlier, but with f transpose instead. So now we use a key property of the transpose, which is that the transpose and the powers are interchangeable. And this is true because, well, this is a loose end actually. We could show this by induction again and matrix multiplication, but that's like it's technically true, but you know, what is it really saying? From what I know, a way of understanding this result intuitively is actually in part 3 about we could prove it by thinking of transpose as what is called the adjoint. Okay, so we're going to interchange everything. Okay, and since transpose is linear, we could take the entire transpose and put it on the outside. And so we just showed that any polynomial of f transpose is that same polynomial applied to f and transposed everything. So polynomial application is interchangeable with transpose, which is very cool. And let's consider what happens with the vanishing polynomial. So with a vanishing polynomial, p of f transpose is equal to p of f transpose. And since p of f is 0 transpose, well, 0 transpose is just 0. So all this means is that any vanishing polynomial of f transpose is also a vanishing polynomial of f. And so let's consider what we have so far. We have that the eigenvalues of a linear map are included in the roots of any vanishing polynomial of it. And we have that vanishing polynomials of f are the same as vanishing polynomials of its transpose. So to fit all this together, to show that the eigenvalues are the same, it starts becoming natural to think, okay, this subset relationship, that the eigenvalues are a subset of the roots, could we make that an equality? Could we make it so that, could we find a vanishing polynomial where its roots are precisely the eigenvalues of f? Because if we were to do that, let's see what happens. We would have that the eigenvalues of f are equal to the roots of this polynomial, this vanishing polynomial. And since this vanishing polynomial is shared between f and f transpose, the roots of this vanishing polynomial must also equal the eigenvalues of f transpose. And so we're done. These two make a big horseshoe-shaped equal sign. So when is this true? When is this subset relationship true equality? Well, then this allows us to start doing some investigations and thinking. And we might just then stumble upon this concept called the minimum polynomial. The minimum polynomial of a linear map is the unique polynomial of minimum degree that vanishes it. Let me say that again. So we consider the vanishing polynomials of f. We look at the one that has the smallest degree as a polynomial. And we discover that there is only one polynomial of the smallest degree. And that this minimum polynomial has the property that its roots are precisely the eigenvalues of f. This is exciting stuff. And although I'm leaving it out here, at this point it is quite natural for us to want to investigate this. When is this subset thing an equality? And so I like this more than the determinant stuff we were doing last time. And in a future video, I'll talk more about vanishing polynomials, because there's some exciting links with order theory. Okay, so this is the second way. I like how it's actually illuminating connections between polynomials and linear maps and eigenvalues in a way that the previous one didn't, and how it gives us a natural route or a natural plan of attack to prove this result that we had without really difficult to understand or without unintuitive things going on. Although there was that one loose end, which is why is it that transpose and power can interchange? For that, let's take a break, refill your drink, And that will be next time.